Hello and welcome to Physical Sciences. Today we're focusing our attention on electrostatics. But which part of electrostatics exactly do we want to focus our attention on? We shall be looking into the basics of exactly how materials or objects become charged in nature. So the key focus in this case is to look at the nature of charge. How does charge arise? And what exactly do we mean when we say a material carries, for argument's sake, a negative charge, or alternatively a positive charge? Or it could be a case where we're saying that a material is actually neutral. So we shall try and break it down in the easiest possible way that we can, so that we try and bring some understanding on the concepts of charge, right? Without any waste of time, let's look at the overview in terms of the thinking. Okay, so the big question that is going to guide our discussion today is the thought around how objects become charged, either positively or negatively. So how does a material acquire a certain type of charge? So already it points out that we have got two categories of charge. It could either be positive or negative, and the conjunction or suggests that it can be one of the two, not both. Okay, and then the second point for our thought for the day is what determines the magnitude of charge. So we are worried about how big a charge is. So when we talk about magnitude, we actually talking about the size that it carries, a material carries in terms of the charge. Now, from a specific type of material that we shall use that. Now, in terms of the concept, right, what we already know, or the assumption of what exactly we already know, is that we talk about the physical properties of materials in terms of conductors. So when you talk of conductors, what exactly are you talking about? You're talking about electrical conductivity in this context. So conductors are essentially materials that allow charge to be transmitted through them, or they can carry charge from one material to the next. So we refer to those materials in terms of physical properties, that these materials are electrical conductors, because in a different context we may talk of thermal conductors, which obviously has to do with what? With heat, right? In the opposite end of conductors, we've got insulators. What are insulators? Insulators, actually, in terms of physical properties, they display or they exhibit the opposite of conductors. These are materials that actually exclude charge or do not allow charge to be transmitted through them. However, there's something that's quite unique about insulators as far as static electricity is concerned, which is something which will form part of our discussion for today. But the key idea is around the origin of charge. So the origin of charge, we talk about either positive or negative. How does the material become positive or negatively charged? So that's the big idea in terms of today's session, right? Okay, now the terminology in terms of the keywords, science is a language on its own. So the language in terms of how we use it in science would definitely differ from the everyday spoken language. So terminology, a very, very critical component of science, which forms the basis of our understanding. So that much said, we also want to appreciate the fact that, when you look at the definitions, it's either all or nothing. It's either you're given the 2 marks or nothing. In some cases, you may be given a statement and then you must identify the correct term. You are still matching, the description to the appropriate definition. So it's all or nothing. The examination guidelines are there for us to refer in terms of what is acceptable as far as definitions are concerned, right? So the first keyword that obviously this has got to do with the big idea of electrostatics. Now we talk about static electricity, or we deal with charges, okay? But what's so important about charges here is that these charges are actually stationary, okay? Charges that are stationary, okay? Not moving in the context of flowing, which is what distinguishes electrostatics and electricity. So the word static suggests that the charge is stationary. And then the word electro suggests something about charge, and this is about electrons essentially, okay? So electrostatics is actually that branch of physics that deals with stationary charge and, you know, the effect of charge in terms of the fields, you know, it goes on and on, but basically the long and short of it, it suggests that it talks about stationary charge. And then the second term deals with the law of conservation of charge. And in physics, there are a lot of laws which guides our understanding in terms of the theory, which also has far-reaching implications in as far as the application. But now, when something is conserved, you know, you'd realize that with all these principles or law that suggest something about conservation, they essentially say to us that, okay, there is a certain aspect, usually it's in a closed system, or a certain quantity that remains constant. A quantity is anything that can be measured, you know. Charge can be quantified. We shall talk to that at a later stage. But when we say the law of conservation of charge, we actually refer to exactly what happens when materials interact with each other in terms of charges. And the quantity of charge, which is the total, the net, remains constant. When something remains constant, the key idea is that that particular quantity does not change. Okay, or it is conserved, put simply, right? And then the other term is quantization of charge. This is a very, very important aspect of, you know, determining the magnitude of charge. And this has a lot to do with how do we determine, okay? This has a lot to do with how we determine the amount of charge carried by a material. So I'll put it as a question for now. How do we determine the magnitude of charge, right? The magnitude of charge on an object, okay? Right. So this law is you know, is fundamentally key in the sense that it guides us in terms of saying, when we say something has got a certain amount of charge, you know, in terms of how charge arises, it will give us an indication of whether electrons were removed from it or electrons were actually added to it. But it also speaks to the number of electrons. So that's the language that we're gonna talk about. So the net charge has a lot to do with the law of conservation of charge. The word net on its own suggests that it's the total, it's a sum, it's an addition. So the word net is one of those key words across many of the topics in science that obviously, you know, talk about the resultant charge. You know, we can talk about the total charge, the sum of charge within a system that is given. So the word net is going to be used once too often than others. But take note, the word net suggests the sum or total, right? So net charge talks about total charge, okay? It talks about total charge, okay? Take note of that. And then triboelectric charge. This has to do with, you know, insulators, materials. We shall make a demonstration in due course, which shows how materials are charged. So when two materials come into contact with each other, you know, there could be friction, you know, the force exerted by one surface on another, and when that happens, charge is transferred between two materials in a physical process, and that has a lot to do with, you know, the principle or the law of conservation of charge. So when something is triboelectrically charged, it means those two materials came into contact, and as a result of that, one acquired more charge, and you know, if one of them, say for argument's sake, was neutral, the other one transfers the charge, and then this one that becomes charged would describe it in terms of it being triboelectrically charged. So that's the gist of what exactly we mean by that, right? And then so this is the origin of charge. That's the main idea that we want to entertain. Having said that, let's move on to, you know, how exactly charge arises. So a neutral material, so if something is neutral, what exactly does it mean? If something is neutral, it is uncharged, okay? It carries no charge, right? Now, we need to be very careful around neutral materials or objects. It carries no a net charge. In other words, the net charge is equals to 0, okay? So if it carries no net charge, it means zero net charge. Now, if the net is zero, remember, any matter, as we know it from an elementary level, consists of subatomic particles, your protons, your electrons, your neutrons, you name them. And each one of these, the proton is positive, the electron is negative, the neutron, as the name suggests, it's neutral, okay? Now, if the number of positive charges equals the number of negative charges, the net charge is zero. But wait a minute, does it exactly mean that, in other words, there are no charges? Definitely not. It means the net charge equals to zero. It means there is an equal number of positive to negative, right? So that's what we mean when we say there is an equal number. So the net charge is equals to zero. So if it's neutral, that's the implication of that. So if, for argument's sake, we add electrons to a neutral material, it has what is called excess electrons, what we would describe as excess electrons. Now, if something has excess electrons, it doesn't mean that it doesn't have positive charges. It means there is more negative charges than positive, right? And then also, on the other hand, we've got what is called polarization. A material may be neutral. However, the distribution of the charge will be such that one end of that material has an accumulation or a collection of positive, okay, while the other end has got an accumulation of negative. The net charge here is zero. However, one end of the polarized material becomes negatively charged, while the other end becomes positive. This is typically what happens with water molecules, okay? Water molecules are polar. It means they are actually polarized. This is one perfect example of what polarization is all about, okay? And then what happens if a material loses electrons? Now, suppose initially the number of electrons equals the number of protons in a material. Now, it also suggests that the material is actually neutral. So what if we remove some electrons? It means there will be excess protons. But the excess protons were not a result of adding protons, okay? Let's go back, rewind. If we go back again to the atomic model, the structure of the atom, you'd understand that the electrons occupy these orbitals, this energy level. So it's easier, it's actually practical to knock out electrons or bring in electrons than to add positive charges or remove them either, okay? So if we lose electrons, what's going to happen? The material becomes positively charged. So if it is positively charged, it means it has excess protons. But these protons were not added. What actually happened is we removed the negative charges. So that's how a positive charge arises on a material as well as a negative charge. So negative is a consequence of gain of electrons, while positive is a consequence of loss of electrons, right? Okay. Having said that, we also know that there is interaction between opposite charges. They exert a force on each other. Opposite charges, they tend to attract, while if they are alike, they tend to repel, right? Okay, so this is in terms of the forces. But now, if we can quickly summarize what the concept or the idea of how charge arises. And now when we talk about charge, we talk about positive as well as negative, okay? These are the two classes of charge which you need to keep in mind. There's positive as well as negative, right? So all forms of matter contain three subatomic particles: protons, which are positive, electrons, which are negative, and neutrons, which are neutral, okay? So remember, electrostatics has to do with the movement of electrons. Electrostatics, okay? So the charge arises as a result of removal or addition. So if we remove, it's going to be a positive charge, okay? If we add electrons, the material becomes negative. That's how charge arises. But keep in mind that neutral materials have a zero net charge, which does not suggest that they have no charges. Having said that, let's take a short breather, and then we'll go deeper into detail and look at how these charged materials interact with each other in as far as the principle of conservation of charge. Let's take a short break for now. Welcome back to our second segment. We're still discussing electrostatics with our focus on the origin of charge and how charged materials actually interact with each other in space in terms of the law of conservation of charge. These are the two big ideas for the purpose of today's session. Having said that, let's just quickly recap in terms of how the negative and the positive charges arise. These are the two classes or categories of charge that exist, right? So we said that an object acquires a charge through transfer of electrons, and the word transfer suggests that there can be a gain, okay? Alternatively, we say addition. If something gains, so it means the process of addition of electrons would have taken place, or it could also include, the loss, right? Which is removal, right? So the language there is very, very important. So if something gains electrons, it acquires a negative charge, right? So the negative charge has to do with the gain of electrons. Okay, so the transfer is actually about one material losing and the other material gaining. So the one that loses would actually become positive. So the loss or removal of electrons from a material results in a positive charge. Okay, results in a positive charge. Okay, simple and straightforward. And then a positive charge is about loss. We agree to that, okay? And then a negative charge has to do with the gain. So when there's loss and gain, there's actually the transfer, right? So that's as far as origin of charge is concerned, okay? Now, let's look at conservation of charge. We've managed to briefly, unpack the term conservation. If something is conserved, it means it remains constant, okay? It remains constant. It could be with respect to size or magnitude, okay? So if something remains constant, we can describe it, using the term conservation or conserved. Okay, so when an object gains or loses, so this is one of the two possibilities. We do not have both of them at the same time. So there is gain when you add electrons, or there is loss when you remove electrons. So the total number of electrons gains is the same. This is what actually this statement suggests. Just to break it down, we are saying that if material A has got X number of electrons and in excess, and then say for argument's sake material B has got a certain number of protons as an example in excess, it means A is negatively charged while B is positively charged. So when we talk about transfer of charge between material A and B, we are essentially saying that whatever A loses is exactly what B gains. So even in everyday life, if I give you a 10 rand, I've lost 10 rand, okay, but you have gained 10 rand. So whatever is lost is equals to what is gained is essentially what is transferred between the two. So that's the long and short of it. And then it says here, the charge cannot be created or destroyed. Okay, so we are very familiar with this statement. So if we say charge cannot be created or destroyed, we're saying that charge, this can only be possible if we talk of a transfer. Okay, so if transfer, whatever is lost is equals to what is gained, but the net remains the same. So here when we say charge remains the same, we're talking about the net charge. Be mindful of that. Okay, the net charge is actually the total charge. Okay, right. Having said that, okay, there's another thought again that we just want to remind ourselves of. We have managed to look at how objects become negatively or positively charged. We're fine with that. Now, how then what exactly determines the charge on a material? Now that we know that the material can either be positive or negatively charged. Now, in terms of magnitude, which is the size of charge or how big the charge, because charge will obviously vary from one material to the next, depending on the number of electrons added or number of electrons removed during the transfer. Okay, so what determines the size of the charge on an object made from a specific type of material? So this is the big question that we want to address, and this couldn't be further from the fact that this has a lot to do with the conservation of charge, where we talk about the net charge, right? Now, already we are here in terms of our concept map. So this is the aspect that we want to address now, to say what exactly happens when we talk about a closed system wherein charge or net charge remains constant or is conserved. What exactly are we talking about? Right, okay. Having said that, okay, transfer of charge between of electrons, because what exactly moves are the electrons, not protons, okay? It happens through contact or friction during a physical process. Okay, let's just try and break this down. When we talk about a physical process, we are saying that there are two materials, and at some point or the other, for charge to be transferred, these materials need to come into contact. And to facilitate or to enable the transfer of material of electrons between material A and material B, there must be some form of friction, to knock off electrons from A to B or B to A, whichever the case may be. But that's what we exactly mean when we talk about a physical process. All right. So insulators, they store or conserve charge. Okay, because this is a physical process. Property of a particular material. So charge stays stationary on the surface of an insulator. This is, for example, your clothes or your hair. Let's make a specific example. If you comb your dry hair in the morning, what happens is there's friction. There's that physical process of contact between the comb and your hair. In the process, the comb or your hair may become charged. Okay, because charge has been transferred during that contact or that physical process. Okay, now which also it reminds me of another perfect example. If you take off your jersey on a hot summer day, when the air is dry, there's a friction that happens which occurs between the surface of your body and the clothes, and then you hear those sounds. It's like sparks. Even if it's in the dark, there will be sparks. That's the process of charging. That's what we talk about when we refer to the physical process in terms of the transfer of charge. All right. Okay. Now we just want to look at a simulation, which is a practical example of how materials are charged and what happens when there's discharging. Discharging is actually, removing the charge that is accumulated. So I would use a simulation in this case to try and show that our observation. This is actually, an everyday life observation. It explains the science, that we observe, almost on a daily basis, which also serves to say to us that, the science that we learn in class is actually around us. It's very much alive. We just need to pay attention and try to, have the thinking of science behind to say, okay, how then do I explain this observation? So this is a very familiar observation. We'll talk about the science behind what you see when this happens. Okay, so we've got a gentleman there, John Travolta. That's the name of the Travoltage. That's the name of the simulation. Okay, now John is standing on the surface of a mat. The mat on itself is an insulator. Remember, in terms of physical properties, insulators, they don't allow charge to be transmitted through them. But because of contact, if John moves his foot, look at what is happening. Look at what is happening there. Charge is accumulating on John's body, but there are some very important observations that you need to take note of. For charge to be transferred from the carpet to John, there was supposed to be contact between John's foot, which is an insulator, and the carpet, another insulator. Now, as he was rubbing, this is typically what happens when you walk even barefoot across the carpet in a room. And then John is charged. Okay, the charge, that excess charge that John has acquired is actually from the carpet. Now, if John touches the metal door handle, and the metal door handle is actually a conductor, then the discharging process will occur. Look at that. So all the charge that John accumulated has been discharged. That's where you experience that minor shock, so that's static electricity in action. Just to repeat that, so the more he keeps rubbing his foot, the greater the quantity of charge that John acquires. So John is gaining electrons. There's lots of electrons there, as you can see. Now, John is charged. Even if he was to touch somebody else, okay, the discharge process will take place, because again, that's another physical process. There's also contact. So the discharging happens when he makes contact with a material that is an electrical conductor, right? So hopefully that makes some bit of sense in terms of the simulation. Just to explain what exactly happens in the process of charging. So transfer of charge between materials, okay, electrons move, they okay through the contact. So we've spoken about the physical process. The discharging part we saw, it takes place when we touch a conductor. So the insulator accumulated charge through friction. That was a physical process. Charge was transferred from one material to the next. The one that acquired the negative electrons became negatively charged, while the one that lost became positively charged. So in essence, we are saying that John acquires a negative charge because electrons were transferred from the mat to John, while the carpet itself attained or actually got positively charged. So these charges, they move through the conductor to the earth. This is what is called discharging, okay? Or in other words, the earthing, okay? Right. So we've also referred to this term triboelectric charging. This is actually what happens when charge is transferred between two materials, and these materials are usually your insulators. So pay careful attention to this term. You may be asked to define what triboelectric charging is. So triboelectric charging essentially has to do with transfer of electrons between two insulators, okay, such that one becomes negatively charged. And again, you need also to realize that this is only possible when two materials come into contact. And the triboelectric series actually speaks about, you know, the different materials that can be charged in the same way. But remember, their readiness to acquire that charge will depend on the type of material. So some become easily charged, while some they need a lot of, you know, friction. So that series actually breaks it down to say, within this list of collection of materials, which one actually becomes easily charged. So that's what triboelectric charging is all about. Okay, right. So having said that, so this was the main concept around conservation, leading to conservation of charge. That the charge remains the same, however, it's transferred between two materials. All right. Having said that, let's take a short break, and then when we come back, we actually want to look deeper into how conservation of charge actually happens, you know, when we quantize charge, or we talk about a specific amount of charge between two materials coming together in a physical process. So we shall make a number of predictions in an attempt for us to understand exactly what happens when we talk about, or the application of the principle of conservation of charge. Let's take a short break for now. Welcome back to our third and final segment. We're still talking electrostatics, charges, the origin of charge, and how charge is acquired in terms of two materials coming into contact with each other. As a result of that, one acquires, you know, a certain amount of charge. But now we just want to focus our attention on what affects the magnitude of charge when, you know, charge is transferred between two materials, right? So naturally we know that any two charged materials, they exert an electrostatic force on each other, and this electrostatic force is very important for us to also identify it as a non-contact force, right? Be careful, we are talking non-contact electrostatic force, not the charging. The charging, there has to be contact, but once they are charged and separated, they actually exert a force on each other without them being in contact. So this non-contact force, we'll refer to it also as a field force, okay? So this non-contact force is actually a field force. So what do we know already from, you know, our earlier grades? That opposite charges attract each other. Opposite, we're talking about positive and negative, okay, or negative and positive, whichever comes first. The order is not important. As long as they are opposite, they would exert a force of attraction towards each other. Okay, then like charges, they tend to repel each other. Okay, like, what do you mean? Positive and positive, they exert a force on each other. Okay, away, they tend to push away, while opposite, they tend to pull together. So remember, as you know it, a force is a push or a pull. So these are the pushing, these are pulling together. And this can also be a similar case with the negative charges. They also exert an electrostatic force of repulsion on each other. So the key terms is attract and repel. Right. Okay. And then once more, these neutral materials, they certainly carry a charge. However, the net charge in a neutral material is equals to 0. We're still emphasizing that fact to say here that it doesn't mean that there are no charges. Okay, it says to us that the net charge is actually equal to 0. Okay, is equal to 0. What does this mean? It means that the number of positive charges equals the number of negative charges. Okay, but if you look at the balloon in this snippet, it has got the same number of positive charges as the negative charges. But what does this tell us? It tells us that it's neutral, but there are charges as you can see them. However, if we bring this this neutral balloon towards this neutral jersey, because of the charges, there will be forces that will act on each other on these two materials. Why? Because we've spoken about polarization. And polarization actually has to do with forces between like or opposite charges. So why are we saying that there will be forces here? So if we draw this balloon closer, the negative charges on the balloon will actually attract the positive on the jersey, while at the same time repelling or pushing away the negative charges on the jersey. So there will be a force between these two that acts both attraction as well as repulsion. Okay. Right. And then another very common observation happens when we bring a charged material closer to a neutral one without making contact. And remember, we spoke about field forces, field or non-contact forces. Okay, these are field or non-contact forces. They still exist even between polar materials. So the stream of water, we said water is polar. Okay, what does it mean? It means actually we're talking about water molecules. It means that there are certain portions of the water molecule that are slightly positive, others are slightly negative. So what happens when you bring a charged material? Let's say the surface of this comb is positive, for argument's sake. It has got a positive charge, or it has lost electrons. Okay, so if you bring it closer, the positive charges in the comb will actually repel the positive charges in the polar water molecule while attracting the negatives, which explains why this smooth stream of water actually is attracted to the comb. So this actually, this flow of water, we'll call it the laminar flow. So that's the term that is used to describe the flow of water in that stream. But because of the polarity of water, here the force does exist between the comb and the polar water molecules. Why? Because these are field or non-contact electrostatic forces. Right. Okay. Moving further, we're still talking conservation and quantization of charge. Now, when we talk about quantization of charge, we want to determine what determines the magnitude of charge. So quantization of charge has to do with magnitude of charge. Okay, it explains how we arrive at a certain magnitude of charge. Okay, and remember, the word magnitude suggests size. Okay, so if a material loses, let's say 20 electrons, okay, it becomes positive. While again, if a material loses half that number of electrons, 10 electrons, it also becomes positive. But the extent of the positive charge will obviously vary based on the number of electrons that were removed or that were added to acquire that negative charge. Remember, we spoke at length about that in as far as the origin of charge is concerned. Right. So this is one other aspect that we want to look at. Now, very, very important build up to the quantization of charge. It says the elementary charge of one electron. So a single electron has got a charge of negative 1,6 times 10 exponent negative 19. Now let's break it down. This negative is for the charge that it's negative. Okay, right. But this negative is for the decimal fraction. Okay, let's not confuse the two. Right. Now here it means we're dividing by 10, 1.6. We're dividing it by 10 exponent negative 19 coulombs. That's essentially what we are saying. All right. Now, it says for material to acquire a negative charge, electrons have to be added. But the magnitude of the charge that will arise will actually depend on the number of electrons that were added to achieve or to acquire or attain that negative charge. So what is the magnitude of the charge if one electron is added to an insulator? Now, the assumption is that we have an insulator with us. Now, on this insulator, we add one electron. There is no question about whether it becomes positive or negative, because we have added electrons, then it becomes negatively charged. But now the question is, if we add one electron, it means that there is one extra electrons than protons. Or in other words, there is one electron in excess. That's exactly what we are saying. But now, it doesn't mean there are no positive charges. Definitely not. The number of positive charges is actually one less than those of protons. So what if we add one electron? If it was neutral, now it means the charge is equal to the number of electrons that we added multiplied by the charge of a single electron. That's what it is. Because when the equal number of electrons and protons, then the net charge is equal to 0 on that material. So here, because charge, the symbol for charge is Q, that's very, very important. Charge is Q, that's the symbol. The unit is the coulomb, okay? So symbol for charge is Q, okay? And then unit, SI unit is the coulomb, okay? The unit is the coulomb. Okay. Now they will talk about later some different types of units. Okay. So there is one electron that was added. Okay. What's the charge of this extra electron? Negative 1,6 times 10 exponent negative 19. Okay. Now the charge on this one will actually be equals to negative 1,6 times 10 exponent negative 19 coulombs. Okay. So the number of electrons that we add to a neutral material actually determines the resultant charge after that. Okay. Let's continue with our predictions. Right. Now, what is the magnitude of charge if 10 electrons are added? Okay. Now, if we add 10 electrons, the charge becomes NQE. Okay. This is actually what the principle of charge, quantization of charge, that's how we represent it mathematically. Now, the charge is equal to how many electrons were added in this case? 10. So we added 10. Now, if we added, it means it's going to be negative 1,6. That's the elementary charge. Negative 19, which is a constant. It won't change, right? So if we multiply that by, it actually gives us a charge of 16 times 10 exponent negative 19, okay, coulombs. All right. So that's exactly what happens there, and we are saying that even if we put it to one decimal place, this then will be equals to negative 18. Okay. Just to confirm that. So if you multiply it by 10, it's like you're saying 10 exponent 1. So negative 19 plus 1, it gives you negative 18 from your laws of exponents. That's a bit of maths, but the science is essentially in the principle of quantization of charge. Now, we're getting the pattern or the trend. Now, if there are 500 electrons added, so it means N, which represents the number of electrons added, is equals to 500. Okay, so the number is actually just a number, it doesn't have units. So I'll just say 500 electrons were added, then we can immediately predict that Q is equals to 500, okay, multiplied by negative 1,6 times 10 exponent negative 19. Okay, so whatever that reduces to, that's the magnitude of the charge. So you'd realize that the extent of negative charge increases as we remove the highest number of electrons. Okay, so if we remove 10 and we remove 500 electrons, in both cases the charge will actually be negative, but the extent of the negative charge actually is influenced by the number of electrons removed or added in that case, which takes us to the next part, which says the elementary charge still the same constant that we are given. Okay, so for a material to acquire positive charge, electrons must be removed. We've been saying this, many times before. Now it says, what is the magnitude of the charge if one electron is removed? There's something very, very critical in as far as this part of the discussion is concerned. Now, can we think of it this way? If the number of electrons equals the number of protons, what are we saying? We're saying that the net charge is equals to 0. So if the net charge is 0, it suggests that then the charge that a proton carries is the same as that of the electron. However, it's positive. So that's the main thing. So as we remove electrons, we're saying it becomes positive. So if we remove one electron, Q, that's the charge, is equals to N, which in this case represents the number of electrons removed multiplied by the charge of an electron. But this charge of the electron which is removed, it means then Q is equals to 1 electron removed. Then if we remove the electron, it becomes positive 1,6 times 10 exponent negative 19 coulombs, right? So then our Q is equals to positive 1,6 multiplied by 10 exponent negative 19 coulombs. Remember that negative is for the decimal fraction, but essentially this charge is positive. Okay, and then it goes further and says here that what if we remove 20 electrons? Now we are saying N is equals to 20 electrons removed. Okay, just to qualify that 20 electrons removed, right? So we go back to the quantization. Q is equals to NQE, all right? So Q is equals to 20 multiplied by positive 1,6. Because we've removed electrons, the charge that results is positive, very important, multiplied by 10 exponent negative 19 coulombs, right? So this is actually giving us the actual charge. So if we go to our calculator, we can immediately say, okay, we've got 20 multiplied by positive 1,6 times 10 exponent negative 19. You also need to familiarize yourself with using the calculator. So this is 3,2 times 10 exponent negative 18. Okay, this is Q is equals to 3,2 times 10 exponent 18. Okay, so this is 3,2 times 10 exponent negative 18 coulombs. So we can immediately pick up that trend to say the charge will definitely be determined by the amount of electrons added or removed. So to arrive at the principle of quantization of charge, ultimately we are saying that every charge in the universe is actually an integer multiple of the elementary charge, which takes us to this mathematical equation, which is actually what the principle of quantization of charge is all about. And remember, mathematically an integer is a whole number, okay? So the number of electrons cannot be 1.5, 3.2. It should be, a counting number of electrons added or removed, right? Okay, so that's basically the main idea in as far as the principle is concerned, right? So we've managed to look at quantization of charge, right? Origins of charge, and as well as the conservation of charge. So all matter is made up of positive and negative subatomic particles, but remember, the transfer is actually about the electrons, Right. Having said that, I think we getting the gist in as far as the two main thinking ideas that we started with, to say how exactly charge originates, be it positive or negative, in terms of transfer, which also entails loss or gain, as well as what exactly determines the amount of charge that a material acquires based on the number of electrons removed or added. So that's how we arrived at the concept of how charge is quantized in terms of the number of electrons removed or added. That gives us that the charge is actually in multiples of the number of electrons added or removed. Having said that, and because of time constraints, that's the only time that we have to cover the ground that we've covered for just for today. From myself, Themba Ncube, cheers and bye-bye for now.